Welcome back. Quick recall from the last video. We were studying the introduction to the component form of the cross product. We were saying that the entire idea of the cross product is to take two vectors in R3 and produce a vector in R3. We also said in the last video that the cross product has two major purposes, one of which is to measure perpendicularity. Recall that we had this concept that the cross product had two arguments, the first argument here and the second argument. And we said that this was actually really hard to do in general as the first step to studying this problem, to figure out how to measure perpendicularity of vectors in R3. But we might start developing intuition by studying a related problem, which is how do you measure perpendicularity in R2 when you have two vectors and you're comparing them? In particular, we want to come up with a measurement to quantify how perpendicular is x to y. In order to do so, let's go ahead and graph this general combination of vectors. So we have a vector x1, y1, and a vector x2, y2. They're on the first and second coordinate axis. I'll go ahead and zoom in here just so you can see this again. Sorry about that. So we're going to introduce a pretty crazy concept here, which is that perpendicularity between these two vectors really has to do with this angle theta. The closer theta is to 90, the more perpendicular these things are. The farther away from 90, the less perpendicular it is. What's interesting about this is a priori, a priori means before we've investigated, if we only have these components, we don't know what the angle is. When we're constructing the cross product, we're going to try to construct a formula for the cross product that does not depend on the angle, only the components that we're given. Because of this, I want to introduce a very useful concept, which is that there is a connection between this angle right here, the angle that we care about to measure perpendicularity, and the area of this parallelogram. Notice this gets back to the definition of vector addition. So here you have x. Here we'll go ahead and add y to x. So here's x plus y. Here is y plus x. And these together form the vector that goes along the diagonal called x plus y. What's interesting about this is we could use the area of this parallelogram as a proxy measurement for perpendicularity. So major intuition behind the cross product. The area of the above parallelogram is a good proxy substitute measurement for perpendicularity of angle theta. Let me explain what I mean by this. What would happen if we start to bring these two vectors together? Do you see that the area of that would kind of shrink? Right? The inside area would get smaller because it's getting thinner, and we'll actually quantify this in a second. What would happen instead if I let these things go closer and closer to 90 degrees? You see it turns into almost a square or a rectangle? The only way it would be a square if these lengths were the same, but it's certainly a rectangle, right? Which means the area gets larger. So the area of this parallelogram is largest when theta is 90 degrees. and it is smallest when theta is 0. Indeed, if theta is 0, you have 0 area. And that goes back to the exact thing we were just saying. We want a measurement that's largest when the two vectors are perpendicular, somewhat less when they're in between, and then 0 when they are parallel. And the area of this parallelogram actually gives us exactly what we want there. So the question that we have is, if we're going to do this, if we're going to say that area of the parallelogram is a great measurement of perpendicularity, the immediate question is, well, yeah, you read my mind. How the heck do you measure area? In order to measure area, we're going to start doing a little bit of annotation in this diagram. And this is where I'm starting to twitch a little bit because I don't have my ruler. So I have to do it by hand, which makes me nervous. Okay, so what I want to show you here is, here is the vector x, and we said that x had two components, x1 and y1. So the height along this area right there is y1. So this height from the bottom up to here, this was y1. This height right there is y1. And then this was the vector y, and notice that the vector y went over x2 units. So this is x2. This, of course, down here would be x2 as well. And then it went up y2 units. So from this little line right there, all the way up there, this would be y2. The immediate question that I have is, well, what is the location of this little tick mark along the x-axis right here? Well, that tick mark must be x1, because I move x1 units along here, plus x2, because I move another x2 units based on the addition of y. So this would be x1 plus x2. Similarly, we could look at the tick mark along the y-axis, and the question will be, what would that tick mark be? Well, notice we first move up y1 units, because that's the y component of x, and then we move an additional y2 units, because that is the y component of y, or the second component of y. So this would be y1 plus y2. Okay. Now, I see two shapes that would make the calculation of the area pretty simple, actually. So the whole idea here is we want to find a way to measure the area of the parallelogram, and we're going to do it by looking at this diagram in a very special way. Shape number one, perhaps in this situation, I should grab my trusty highlighters. Okay, so I'm going to claim that the area of the inside parallelogram, the one that we're going to use to measure perpendicularity, is going to be the area of this green shape, which is the outer edge. Okay. So that's an area that's actually quite easy to find, right? Because that area has 1, 2, 3, 4, 5 things. Or another way to say it has 1, 2, 1 rectangle. And then if we subtract away that green from that green shape, the area of this red shape, right, where the red shape comes down here, we would be left with the area of the thing in between, right? All right, so let's go. I'm going to zoom out a little bit because I want to come back to this diagram throughout this discussion. Okay, so here we go. The area of the parallelogram is equal to the area of the green shape, and I'll go ahead and draw that in just a second, minus the area of the green one, minus the area of the red shape. Okay, so here's the green shape. I move along y, I move along x, and then I just drop this down immediately, and I go here. Inside that green shape, we've got a triangle, and then a rectangle. You can see that outlined here, right? Triangle, triangle, internal rectangle. And then the area of the red shape, well, first the red shape is move along x, move along y. And what's really nice about this is the area of that red shape has a triangle, and a rectangle. Okay. Well, let's go ahead and start to quantify what these areas are actually measured by. So notice that the area of the green shape is going to be 1/2 times base times height. So here we're going to first start in the green shape. We're going to start with this triangle right there, triangle number 1. So this is going to be 1/2 base times height. The base is going to be x2. The height would be y1. So this would be 1/2 base times height. So that's the first triangle. Perhaps we call that 1. So this is the area of triangle 1. See it? Okay. Maybe can I go out a little bit further here so we can see it? Okay. We'll call this thing right here, we'll call it triangle 2. All right. So of course the area of the green shape is also going to include the area of triangle 2. And the area of triangle 2 would be the same idea, 1/2 base times height. But the base of this is the value of x1. Since this is the vector x, this length must be x1. That's the direction in the x in the first coordinate. And then the height would be y1. Oh, I think I made a mistake here. This thing, of course, should be y2, right? Of course, should this be y2 because this is y, so the height there is y2. Okay, so this now right here is called the area of triangle 2. Area of triangle 2. This was the area of triangle 1. And then the one last thing that we have in the green shape is the square, which is this large square right there, right? What is the height of that large square? The height of the large square would be the length of this, which would be y2. And then what about the length here? Well, that length would be the distance from x2 to x1 plus x2, which if we look at this, if I subtract x2 away from x1 plus x2, I just get x1. And that makes sense because this length right here would be x1. Okay, so this was what we said, the area of the large square. And if you're following along at home, I would actually encourage you to really draw this out and do it slowly, because if you get this intuition, you're going to get a lot about the component form of the cross product that we're developing here. These three areas together form the area of the larger green shape in our diagram. All right, I just realized that, of course, I've been saying square and I wrote square. This is not a square, it's a rectangle, right? The height of this thing does not necessarily have to be related to the width of it, because the second coordinate of y is not at all connected to the first coordinate of x, right? So we'll call this the rectangle. All right. The whole idea here, though, is that we were trying to find the area of the parallelogram, this one here. And we said that we could, to do so, we'd find the area of the green shape, the outer large shape, and then we'd subtract away from it the area of the red shape. Well, the area of the red shape was the area of triangle 3, triangle 4, and of course the area of the small rectangle. Let's go ahead and capture that. So to do so, we're going to say, let's subtract away from this. Oops, this is a subtraction, of course. We're going to subtract away from the area of the green shape, the area of the red shape. I'm going to go ahead and fold this over just so that we can very clearly see. Hopefully those of you that are following along at home have this in your notes. All right, so now we want to get the area of the pink shape or the red shape. Let's go ahead and look at the area of triangle 3. Area of triangle 3 is going to be 1/2 base times height. Well, the base of that has length x1. The height of it has length y1. All right, so this was the area of triangle 3. We are going to also subtract away from the total green area the area of triangle 4, which is the one right up here, and that looks like it's going to be 1/2 base times height. Base is x2, height is y2. And then finally, we're going to subtract away from this the area of the small rectangle. I almost fell in the same trap again. The area of the small rectangle is going to be the width of that rectangle. Perhaps we call that x2 times the height of that rectangle, which is y1. So just to make this super clear, this was the area of triangle 4. This right here was the area of the small rectangle. And the whole idea was these three shapes together formed the smaller red shape that we were going to subtract away. And now we take this green shape and subtract away the red shape, and we're left just with the parallelogram formed by the x and y vectors that we highlighted at the beginning. Okay, well, take a look at the math here. Do you see anything that cancels out? The area of triangle 1 was identical to the area of triangle 3 because they were actually the exact same triangle. So those cancel out. The area of triangle 2 was identical to the area of triangle 3 because they were the same triangle. And what we're left with is just x1, y2 minus x2, y1. And if we look back at what this says, the area of the parallelogram, this is what we wanted. This was going to be the area of parallelogram, is now given by this difference, which is the size of the large rectangle, or the area of the large rectangle minus the area of the small rectangle. Notice that when the two vectors are orthogonal, these rectangles, if you suppose they're along the axis, notice the entire thing would just be the large rectangle. And then if the two are right on top of each other, parallel, the small and large rectangles would be identical there. So you see that the largest area, the largest difference would happen when the two vectors are perpendicular, and the smallest difference would happen when they are directly parallel. This is exactly what we wanted. All right, we're going to use this definition now of perpendicularity. This is a proxy measurement for perpendicularity. We're going to use this to develop the cross product. Okay, I hope you're on the edge of your seats. In the next video, this is exactly what we'll do.